All right. Hello, everyone. Welcome to today's first Friday HPC event. This morning, we'll take a shallow dive into the message passing interface, or MPI. I won't say a deep dive. We're just going to cover some basic topics. But MPI is a great tool for increasing efficiency and scalability of parallel workloads on an HPC system. And I hope everyone finds this to be an exciting prospect, and hopefully can come out of today's presentation with some new ideas, maybe a better understanding of how MPI it can improve the scalability of parallel software on HPC systems. So first off, I'd like to introduce Auburn's world-class team of HPC administrators. With the recent addition of Raina and Tom, we now have a team of 6 mostly dedicated research computing professionals to help further your research on our HPC systems. That big yellow email address at the top, hpcadmin@auburn.edu, is probably the best place for any questions or observations, feedback, anything else HPC related that you might have. So if you ever have any questions, comments, or just want to get in touch with us, feel free to send an email there. Because this is sort of a virtual format, normally it would be more interactive, and I'd go around the room and ask people, how they use HPC and what their science discipline is, things like that. Unfortunately, we'll probably have to just keep it a little less interactive. And as far as questions go, if you have any questions as we move through the presentation, probably the best way to do that would be to paste those in the chat window. And then we'll try to field those as we see them come through. Did anybody else, the other admins, have anything to add before we get started on the topic?
No, that's good.
All right. Without further ado, then let's get started. So today I'm just going to start with a brief glance at some of the core concepts of parallel computing in general, a little bit of history to help you understand how things have evolved to the current state, with MPI as what's generally regarded as the de facto standard for HPC scalability. And then we'll dive into some more of the technical details of writing, compiling, and running MPI workloads. So any discussion on the evolution of computing would be incomplete without mention of the classic von Neumann architecture. This is published in 1945. And this system standard is still the same model that computer systems are built upon today. A little more complicated. As usually happens as time goes on, things get more complicated. But you can see the familiar components you might be familiar with here. You have a central processing unit that has some subcomponents that handle the arithmetic operations and facilitate the communication between the various components. Registers that hold certain values that represent the state of the CPU. And of course, you have memory as a primary component, which holds our programs and processes, or the higher level instructions, and the data on which to perform operations. And then lastly, you have that system bus, which is sort of the internal connectivity between these components, the wires, so to speak, that the electrons travel across. But from this basic von Neumann architecture, a number of advancements have occurred over the years. In regard to parallel computing in the 1960s, what we saw were these large systems. They wanted to maximize the efficiency, and so they came up with things like time sharing, or CPU instruction pipelining type techniques for things like prefetching or look ahead, which gives you some semblance of parallelism and concurrency in these processors. And as time went on, it's 1970s and 80s, the shared memory concept was introduced in the 60s, but wasn't really practical until the 1970s, where they started being able to put multiple processors in a single machine, and then, actually get true parallelism by accessing a shared memory and running processes in a synchronous fashion, or a parallel fashion. As I mentioned, multiprocessors. So they start adding more and more processors to these machines. You get 3 and 4 processors in there. You start getting a little bit more parallelism, and then they started looking at how can we, we've got these, a bunch of these machines. How can we connect them together, through some sort of interconnect networking, and aggregate their power so that we can get much more processing capabilities, computational power out of these machines. And that's the cluster concept, being able to take these sort of individual encapsulated systems and connect them together in a way where you can harness the aggregate power of those. Then, of course, some of you may recognize the folks in this photo to the right. 1990s and 2000s, a lot of great advances. They had started adding more cores to these processors, and that allowed for dense parallelism in a machine. So you could have a single core, but or single processor might have 4, 6, 8 cores, and then you could use those cores to get your parallelism. The message passing interface, message passing model, I should say, was also developed in the 90s. And that's just a way to, as we'll see, use distributed memory so that you can access memory from a disparate machine through passing messages. You had advancements in high-speed networks, and of course some specialized things like GPUs and FPGAs. And that's sort of where we are today with what you see in modern HPC systems. They're typically clusters connected with a high-speed interconnect. And in order to get the scalability across those clusters, people use MPI, or a message passing model. Okay, so just some conceptual things here that might help as we discuss some of the MPI constructs. There's this thing called Flynn's taxonomy, and basically it provides a simple representation of how some of these processors are architected for handling instructions and parallel operations. On the far left there, you have the SIMD architecture model. It's single instruction, multiple data. And so that's where multiple processing units perform operations on different inputs. And in its most primitive form, this is all done in lockstep, synchronously. But this is parallelism in a very pure form where, for instance, the payroll calculation for users A, B, C, and D can be all calculated in parallel. In the second example, multiple instructions, single data, that might perform different calculations on the same data input. I've included this just to be thorough, but this architecture is rarely used. It's typically for systems that need high fault tolerance. One example I saw was that this particular architecture was used in one of the systems on the space shuttle flight control computers. So obviously a high degree of fault tolerance needed there, but it's pretty rarely seen. The third one, MIMD, or multiple instruction, multiple data, is probably best conceptualized as a system that can perform any arbitrary task using any arbitrary data in parallel. At a lower level, this might describe like a multi-core processor with a multi-user operating system where processors are running independently of one another using an associated address space. At a higher level, you could also probably conceptualize this as the way a supercomputer works. You have many different processes or programs running on many different disparate sources of data. And then finally, on the far right, what we see is a superclass of this Flynn's taxonomy, and that's SPMD, single program, multiple data. And this one is, as we'll see, is probably the most representative of how a parallel program employs MPI, single program, multiple data. So just kind of an overview in some of these parallel programming models at a somewhat low level. Another important thing to understand here is that you have these different ways of that programs access memory. So on the left side there, you have a shared memory process where all processes access the same memory address space over a system bus. And so that's it makes programming pretty easy because you don't have to worry about any specific memory address or anything like that, but you do sometimes end up with a bottleneck on that internal bus. And in this case, parallelism is typically achieved through threading. It's not through message passing, and you're normally limited. This normally describes a single encapsulated system where everything can get directly to the memory. On the right side, you have a distributed memory model where each process has its own dedicated memory, and the communication happens instead of a bus over an arbitrary network. And in this case, you get your parallelism through message passing. And so you can see the one that MPI is most likely to be applied to would be the distributed memory model. So just a couple things there: threading versus message passing. And we see this from time to time where people that have threaded programs using things like OpenMP or pthreads want to try to scale out across multiple nodes. And while there are ways to do that, they often involves a pretty complicated and challenging code changes. So important to know that you have threading, which is usually limited to a single encapsulated system. For instance, a compute node that has 20 cores, you can probably have 20 threads, but that's about it. Whereas in the distributed memory model, because you're going over a network, you have access to much more power. You can traverse systems across the network and pass messages from one process to another at a very large scale. So before I wanted to dive into the MPI stuff, I wanted to introduce a few scenarios that we commonly see in HPC, sort of a way to illustrate why MPI is essential for helping to optimize your productivity on an HPC cluster. So I know this slide's rather dense, so instead of me just reading these to you, I'll just pause maybe for a moment and let you read through the scenarios. And maybe it might spark some ideas, or perhaps you may recognize some of this as the way you might approach your workload. And hopefully as we move through the rest of the presentation, you'll see how using MPI can greatly improve the efficiency and scalability of these scenarios. And I will say that there's absolutely nothing wrong or bad about the way these scenarios, these particular researchers that are described here are doing their work. There are just probably ways to make it more efficient. So just pause for maybe a couple minutes and let you guys read through, and then we'll continue on. While we're paused, if any other admins have anything to add, feel free, but maybe a couple minutes just to read through this. Okay, so hopefully that's enough time for everybody to kind of scan through those. But keep those scenarios in mind as we walk through the rest of the presentation. But now we'll really start to focus on MPI, its core concepts and how to use it. So one important thing to remember, and I want everybody to understand, that MPI, it's the message passing interface. It's a standard. So it's a set of rules and guidelines that define how the technology should work. So of course, like all standards, it has many corresponding implementations that adhere to the standard, but MPI itself is a standard. It's a written document that describes how the system should work and what features it should contain. So if you hear someone refer to OpenMPI or MPitch or LAMP MPI, those are implementations of the standard, not technically MPI. It's designed that way so there can be a standards-based approach to implementing the technology, much like is done for other major core technologies like TCP/IP or 802.11x or HTTP, etc. And as such, it ensures that MPI can be portable and ubiquitous across many systems and platforms. The implementations themselves, like I mentioned, OpenMPI, MPitch, can often be viewed as a software stack. It's important to know that MPI implementations typically consist of three components: a software library to use when building your MPI code, a set of compiler wrappers to help interpret the code and convert the source code to binary so that you can use it. And of great importance, it also includes a runtime environment And that sort of functions as middleware that sits in between the running program and the hardware to help facilitate all of the process communications, set up the communicators, and just sort of serve as the broker or the control unit of how an MPI program runs. Main purpose of MPI is fairly obvious: to provide functionality for parallel programs, portability through standards adherence, and to allow for scalability of parallel algorithms by allowing processes running across disparate systems to communicate, i.e. pass messages to one another. So it provides functionality through implementing MPI features in an arbitrary language or platform, and exposes that functionality to the programmers through libraries or modules that they can include in their source code. It promotes portability through its standards-based approach. There are implementations available in a wide range of languages for many different platforms, and because of this, it's, as of now, the de facto standard for scalability in HPC. It's widely implemented, widely used, widely supported. And in terms of scalability, because it uses the distributed memory model like we discussed earlier, remember, distributed memory model allows for data to be exchanged between processes over a network with message passing. It's massively scalable. I think the last time I checked, I'd seen MPI was used successfully, meaning there was still an observable speed up over 1 million CPU cores. And of course, entering the exascale era, they're looking for ways to even, make that, scale that out even further. And the primary motivation for the MPI forum is to standardize and continuously improve the best message passing features conceived in the research community. Okay, so once again, it's designed to allow parallelism across interconnected encapsulated systems, i.e. distributed memory. You have this concept of the multiple execution of the same program across multiple processes, that single program, multiple data taxonomy item that we saw earlier. And within this environment, this MPI runtime, these multiple processes that are spinning up and executing this program across multiple processes are assigned ranks, and those ranks can be determined by your program during runtime. And so that allows you to say, okay, I want this group of ranks, these process numbers to do this task. Well, I just want one single process to perform some tasks and all others do something else. And so you can sort of control how your different processes are behaving by detecting the rank and acting upon it that way. And the nice thing about MPI is it provides these communication channels for you. So it has these send-receive operations. It has these collective communication operations like broadcast or all-to-all. And it manages this communication topology for you so that you're sort of abstracted from it a little bit, and it makes it much easier to facilitate that message passing to get your data exchanged between processes. All right, so let's take a look at a first code sample. Very basic MPI program here. The first thing you want to look at, and always want to include in order to add the MPI functionality, this MPI.h library. If you have compiled and installed a version of an implementation of MPI, for example, OpenMPI on your system, this MPI.h header file should be available for use. On Hopper or most of the clusters you'll use here at Auburn, it would be more of a matter of doing a module load, OpenMPI, whatever version you want to use. And then that'll set your environment to have this MPI.h in the include path so that you can just add it to your C program. But you have to have that in order to use these MPI functions in your code. The first thing you do when you want to start working with MPI is you have to initialize it. In this case, we're passing 2 null parameters to MPI, and that you can pass an argc and argv, but I rarely see that used. But the main thing is that before you can use any of the MPI features, you have to initialize the environment with this function. Okay, so I mentioned briefly communicators. So MPI logically defines this group of processes or groups of processes as a communicator. By default, it creates an MPI_com_world communicator that you see there. And that basically is just every process that you've asked for. So if you do an MPI run dash NP10, as you see on the side over here, that's number of processes 10. Your MPI com world is going to consist of 10 processes. This MPI com size function is going to pull the MPI com world variable and set this world size variable you've initialized to that size so that you can refer to it later. And so pass by reference. And what you'll see is either C or C++ code in these examples. So for those that aren't very familiar with it, it can sometimes be a little verbose and maybe a little foreign looking, but you know, like most computer languages, it has a lot of the same concepts and constructs. It's just the nuances of it can get a little confusing, you know, when you have things like pointers, or you know, some people don't necessarily recognize pass by reference stuff with an ampersand and things like that. But as you use it more, you get much more familiar with it, much more comfortable with it. But so anyway, these communicators are important to know that MPI groups its processes logically into a communicator, and you can get the size and manipulate these communicators with MPI functions. So I mentioned that already. Default communicator contains all processes. All right, here the MPI underscore com rank, another pass by reference function where you're saying, okay, MPI com rank of this communicator, MPI com world, and then you're passing it this world rank variable, and it's going to, if this function returns, that world rank variable will now contain this process's rank. So it's important to remember, running the same process, the same program over and over again, and however many specified processes, in this case on the right 10, this is going to be assigned from the perspective of this process. So for instance, if this particular instance was running as process 0, the value would be in world rank would be 0 when it returns. And we can see how that works. You always want to call this MPI finalize when you're done, but you can see how that works over here. We have this print statement. All it's doing is saying hello from MPI process rank %D. We've set our world rank using this pass by reference, and then we're going to print the value, the current value of it, to the screen. And you can see over here it says hello from process 0, 4, 2, 3, 6. And you'll notice that the order is somewhat stochastic. It's random. It all depends on what program returned the fastest. So in this case, it looks like process 0, 4, and 2 were running on some hotter cores or something like that. Somehow or another, they were able to return their from that print function faster than the others. There are ways to synchronize an MPI program so that you don't have race conditions and things like that. But this basic example just sort of gives you an idea. You have this communicator, and you have a rank that's assigned to each process, and you can access those values just with these simple MPI functions here. So we'll take it a little bit further, and let's look at an example where, okay, we're all running the same program here, but you know, no, there are differences in the way these things behave, even though it's all the same program. So again, we have the MPI init, MPI com size, MPI com rank, but we take these two variables here, v1, and we assign it just a 1. And we're going to also take another variable, variable 2, and we're just going to assign it a random number, and the random number is seeded by the world rank. So, you know, we can talk further about random seeding, but that just means if we seed the random number generator with a different number for each process, we shouldn't end up with just all the same number. And over here on the side, you can see we're printing our output here. You'll see, okay, rank 5, its V1 is 1 because we've sort of hard coded that here, but its V2 is this, you know, our long integer here. And the same thing for the remaining of these. So it's important to know, while you're running the same program, they're executing the same code, there are going to be differences sometimes, and how these values are calculated, or what its perspective is, I guess you could say, of state and value. Okay, so we talked about message passing. Obviously, that's an important concept to understand. And in this case, we're going to use a point-to-point blocking communication. Now, blocking meaning when I issue a send operation and to another process that's issuing a receive operation, the program is not going to return until that receive and send operation has completed. So they have asynchronous versions of these calls, but those get a little more complicated. So I just want to start with something simple here. But these are just the point-to-point blocking communication between two processes in an MPI communicator. Over here on the right, you can see the syntax of the MPI send and MPI receive functions. Basically, you pass in, it's a buffer, usually an array or something like that, that holds some kind of data, how many of the values you're going to send, and then a data type of what type of value you're going to send. And you say who you're going to send it to. You can provide things like tags to reference the the type of data or the send operation that you want to further identify or uniquely identify. And then you have to pass it to communicator as well. So looking over in the code, we're going to check. In this case, as I mentioned, you can check for the world rank. So we're going to look here and see if this process world rank is 0, then we want to run these two lines of code. So we only want rank 0 to perform the send operation. And here we've initialized number. This number is nil for everybody, but once it comes in here, world rank 0 sets it to -1. So it's going to send its copy of the number, which is for world rank 0 is -1. It's going to send one number. It's an integer. In this case, it's an MPI int type. And it's going to send this to process 1, tag 0 in this communicator. So then we go down a little further and say, okay, well now, if we're world rank 1, we want to issue a receive operation because, well, I'm the programmer and I know I've just initiated a send operation to 1. This is probably not how you're going to do it in any real world use case, but just to illustrate how the send and receive works. World rank 1 is going to issue a receive. It's also going to use its number variable as the buffer to hold the received value. It's expecting one number, and it's expecting an integer, MPI int. It's expecting to receive from process 0, here that's our source, a tag of 0, and then a communicator. And then you can also create a separate variable to store the status. And in this case, we're using MPI status ignore just to ignore it for now. But you can get the status of a receive. If there was some sort of error or warning, you could store that in this final MPI status variable so that you could check it later to see what happened. But here we'll print after this receive operation is completed. Remember, it's blocking, so it's going to wait until this is done. Once it's done, it'll print, hey, process, what's my world rank, received this number. And anything else, if you're not 0, process 1 is going to say, hey, process blank received nothing from process 0 in MPI finalized. And you can see here in the output, process 1 received number -1 from process 0, 2 and 3 received nothing. So that's just sort of and we'll just walk through it with these animations. Process rank will performed receive, all their processes do this. So that just really illustrates a very basic point-to-point communication between two processes using MPI. So what about collective operations? What if we needed to send information to a bunch of other processes within an MPI program? Well, you can do that with a number of operations, but let's try a broadcast in this case. So a broadcast is typically one process is going to send something to every other process. Now you can do this manually, as we see here at the top. Only process rank 0 is going to send, and it's going to do a loop that's up capped by the world size. So it's going to loop from 1 to world size because we don't want to include 0 in this case. We could include 0, but we don't want to. And it's going to execute this code however many times world size is. And it's going to say, hey, rank 0 in this case, sending to process I. And it's going to issue a send using this number value. Up here it's null. Here we set it to -1. So only rank 0 has -1 as its value for number. We're going to send that in a loop to all other processes. So if world rank 0, it's going to issue all these sends. For everything else, it's going to issue an MPI receive. And it's also going to receive to its number variable using the syntax for the MPI receive that we looked at before. And then it'll print and say what it received. Now, that's the sort of manual way to do it. But MPI, as you'll find as you look through the documentation and code samples and things like that, provides many convenient features for doing these things without all of that heavy lifting. So if we look down here at the bottom, better yet, let's use MPI bcast to do all that work for us. If world rank 0 number is equal to 888, MPI bcast number, it's going to be one integer. The sending process is 0, and it's MPI com world, and that's all you have to do. The way that algorithm works in the background is it handles all the establishment of the send and receive channels, and you can see in the output rank 0 with this. For the top chunk of our code, we see this rank 0 sending to process 1, 2, 3, and then all of a sudden we get this broadcast because the number value here is 888. Oops, let me go back. Number value here is 888. But you see this sort of back and forth between sending this -1 to all other processes, process 0 sending a -1 to all other processes, or the very easy broadcast function, which sends the 888 to all processes. So just some examples of collective operations and how you can now see how you can pass this data around, over the entire communicator pretty efficiently. All right, so those are just a few code examples. Hopefully that's got you a decent introduction on, okay, and maybe I'm starting to piece together exactly how this MPI construct works, and maybe you can see how you might use it. But as I mentioned, it's not just libraries and code. It also becomes a stack of tools, one of which is a compiler, or a compiler wrapper is what they call it. And most implementations will provide a compiler wrappers or special flags to help interpret the MPI code. For Auburn systems, modules are available to help set your environment for that. So you just do a module load, open MPI, for example. And then you're going to see probably C, C++, Fortran, like it's going to be a language. It's going to be prefixed with MPI and then suffixed with the language you want to use. So here you see, normally you see like MPI CC, MPI C++, MPI F90 for Fortran. And then you'll use those compiler wrappers like you see here in the code snippet below, MPI C++, the name of the source, -O, and then whatever you want to call your output binary. And it's as simple as that, assuming you've written your code well and there's not a bunch of errors and warnings. That's how you compile the code. If you attempt to use something like GCC, it's gonna spit out a bunch of errors saying, I don't understand what this MPI and init business is, and you'll end up having to use the MPI compiler wrappers. For running code after it's been compiled, you have to instantiate any MPI code with this MPI run. Now that's basically the runtime environment that we spoke of. MPI run is just going to sort of sit in between the hardware and the actual software and make sure and help facilitate the communication, establish all these processes and channels. And so that's why you need to use it. Typically in its most basic form, you just say MPI run -np or -n for number of processors, tell it how many processors you want, and then the name of the executable, and it'll spin up however many cores, run the program, and show your output. There are many other options available you can look at, but for the most part, you really just need to use MPI run with the -np. All right, so I was going to demo some code, but I'm going to take a quick 3-4 minute break. So I'm going to pause for now and kind of let you guys maybe ask some questions in the chat or take a break yourselves, and then we'll get back to maybe running through some demo code, which will be somewhat of a it's off the cuff demo, so it should be interesting. But yeah, I'll be back shortly, about 3-4 minutes.
All right, thanks, Bradley. I don't know if we should let the recording continue or stop it and pick it up. I'm not really sure.
If you stop and start, does it create a new file or does it continue on?
I'm thinking it probably does.
Okay, probably just keep going. Give people a chance to take a restroom break or something.
Well, no, there is a pause, so let's try that.
Okay.
Okay. Hopefully that was enough time for everybody to catch their breath, maybe get a break. So this part of the presentation is going to be a little loose, just because I ran out of time, and I did have some other things I wanted to show, but didn't quite get slides in place, and it's not necessarily going to be very formal. But I did want to walk through another example of how this might be more useful. You've seen some basic ways you can pass messages and things like collective operations, and those are nice. But what are you really doing? You're trying to solve a problem. Most research problems, you're going to have a data set. You're going to need to perform calculations on that data set. You need to have a way to, somehow parallelize the workload, either by breaking the data set up into smaller pieces and having a number of processes act upon a specific chunk of that data, perform its calculation and then send it back, so you can do an aggregate function on it. And this is an example of that. This uses the MPI scatter function. And just what we've seen before, where we have this initialization, we have the com size, com rank. But what we want to do in this case, we're going to create basically this array of integers in C. We'll just consider this our full data set. In this case, it's based on, just for our purposes, it's based on the world size and then this chunk size, which I've set to 5. So if we use 8 processes, that'd be 40. And then we'll have a subdata array that's going to be just the 5 element chunk size. And so the idea would be, and you can extrapolate this out to larger data sets or other potential problems. But the idea is we have this large set of data, and we want to distribute the large set of data across a bunch of worker nodes, worker bees, for example, that have their own little chunk that they want to work on. And so what we do, we're going to go ahead and populate this array with just integers. So this for loop goes through this many times, world size times chunk size, and just adds elements to that array. So you end up with, if we were using a world size of 8, you'd end up with 40 elements. Your data size is probably going to be much larger than that, but for our purposes, 40 elements. And then what we're going to do is issue a scatter operation to take this full data set, MPI scatter here, take this full data set and to distribute it among all other processes. Once we do that and everybody has their own chunk of data, now they can start working on their part. So each of the processes has received, I think, 5 pieces of data, in this case 5 integers, and it can go ahead and start doing some calculations. So this program is going to do something very basic. It's just going to take, each process is going to get their chunk and it's going to calculate the average of their subset of data. So here we go through and we get the total of our subset of data, and then we calculate the average, the total over the size of the data. And then we're going to let everybody know what we found just by printing that out. And so once everybody has their average, we can create another array that holds all of the averages calculated by the subdata blocks, and then we can gather it back. So we issued this scatter, right? And that distributes the data across all the processes. They can perform some operations on them, in this case, calculate the average of what they have, and then send that back to a root process so that it can do something like, oh, okay, I've got these sub averages. Let me just calculate the actual world average based on what my workers have given me. And so that's sort of a basic example of how you might do a parallel workload where you have, it's a very, very simple use case where you have a large data set. You know what calculations you need to do on it. They're fairly simple calculations, not a lot of dependencies on the data or anything like that. Scatter it out to everybody, let them do a portion of the work, and then let them send it back so that you can perform further operations. So we can take a look at how this works. I just so happen to know of a cluster. It's got thousands of cores available for use. You guys can send me a check or something. I can get you the address. But let's see. Let me see if I can actually submit here. Let's run. I got to give it to. All right, I'm right in. And I have this folder here. Let me just walk through this real quick. There's I posted some links in the chat. And if you look there, oops, where's my chat screen? There should be a link for MPI code samples. It's just Auby/MPI. And there's a GitHub repository here that has some of these basic C++ MPI code samples. And if you wanted to get a copy to play around with yourself, you could just copy this URL, and then on Hopper, or if you have a Linux box, you can do a let me get my font size a little bit bigger for you guys here. Is that better? So I just created a directory. You're going to do a git clone, and then that. Oh, that's because I'm on the wrong. I'm on the compute node. Git clone, and then it'll bring this code down so you can work on it. It's in this MPI fundamentals directory. All right, so we have the hello MPI, the MPI bcast, MPI scatter, MPI send. Let's just do the simple one first. So this will be the same for Hopper. Remember, we have to use MPI compilers to build these. If we try to use GCC or something like that, excuse me, yeah, it's going to come up with, I don't know what you're talking about. Although in this case, it looks like it just can't find the header file. But if we do a module load, open MPI, and then let's even try the GCC again. It's probably going to fail. So yeah, it's going to say I don't know what MPI and init is. I don't know what any of these MPI features are. So that you have to use your MPI compilers. And if you take a look in the bin directory, you'll see where all these MPI compilers live. You have C++, regular C, CXX, MPI, Fortran 77, Fortran 90, and that's usually about all you'll find. C, C++, and Fortran. Those are scientific languages that are good for research computing, and so that's normally the ones you'll see. They do have implementations, specialized implementations for other languages that you can find, but for the most part, you'll see those. Those are pretty standard. In this case, we're using C++ code, so we're going to do an MPI C++. Let's do the hello MPI, and we'll call our output file hello. All right, so that came back clean. There were no errors, no warnings. I'm going to assume that compiled correctly, and if I see that I now have this executable binary called hello in my directory, I'm pretty sure that compiled. Now again, if we just try to run this directly, it works, but we're not getting any parallelism. We're not, we only got one process that's doing anything. So we're going to use our MPI run. Let's just try 8 cores here and see what it says now. And okay, that's just like we saw on that slide. The ranks are printing in their numbers, and they're in sort of a random order, depending on who returned first. All right, let's get a little more complicated, and let's do an MPI C++ MPI send. We'll call our output send. You can call it whatever you want. MPI run dash NP. We'll just do 4 for this case. Send. All right. Rank 0 sent number 8 to rank 1. Rank 2 didn't get anything. Rank 1, hello from rank 1, rank 3. Rank 3 didn't get anything, but here we see rank 1 received number 8 from rank 0. All right, take it a little further. Let's try the broadcast. MPI run. And you can see the broadcast operation. Basically a number sent to every process in the communicator. Now for our MPI scatter one, that's the one that's a little more complicated and probably the more realistic way that you would use MPI. See if it'll compile. I worked on this one late last night, so I don't know if it'll compile. It did, miraculously. Let's go ahead and get down to a compute node and start hammering away on this. Okay, so we're in our fundamentals directory. We've got our compiled code here. This one is scatter. Let's try MPI. Let's just start with 8. Let's see, what is this? I'm just going to ignore that for now, but what we see, this is the actual output, scattering 40 integers to 8 processes holding 5 each. So you can see process 2 says, my subdata array index 0 holds the number 10, index 1 is 11, 12, 13, and so on and so forth, and I calculate the average of those, and I get 12. Process 6 is saying, okay, my index 0 is the number 30, 31, 32, and here's my average, so on and so forth, so that you see the perspective from the individual process on what data it received from the scatter operation and its average from the numbers it received. And then below here is after we've gone back and gathered the information back to the root process, and it does the world average overall, all what was found in the sub processes. Now you can try to crank this up a little bit. Let's see if we can do it to 100 cores. IB1. So I think what I have to do in this case, you wouldn't have to do this on Hopper. Have to do this. Maybe IB0. Yeah, there we go. So you can see now we've scaled it out to 100 cores. All right, well that's getting a little bit more meaningful. Now we got a good number of averages to calculate, and you can see each process it gets its chunk of data, its sub allocation of data, performs the averages, shares it back to the root process, who then performs the entire average over the whole communicator. Let's see if we can scale it up even more. Boom. So now we got 200 in play. Let's try something better than that. I don't know if it'll give me 1,000. Keenan and Raina have been working on the system. I think they've handicapped me and trying to keep me from running joyriding in the cluster. We'll have to take it down a little bit from there, I guess. We'll go with 800.
Yeah, I appreciate the Slurm tutorial here too, Bradley.
You bet. All right, I've got 800 cores, so let's try that. This ought to be fun. Now, it takes a little bit longer to initialize when you use these larger number of cores, because that middleware has to work a little harder to gather all that up. But you can see it comes back, and it's scalable. I would expect if I ran the metrics, we'd see a decent speed up if we were to perform the same number of calculations over however many cores. But that's just an illustration, not only one of probably a more likely use case of MPI and how you might do your data allocation and calculations, but also to point out the scalability of it. You're not going to do this with a threaded application without a lot of help and a lot of grunt work and a lot of headaches. But MPI does allow this scalability at a pretty massive level. When you're talking about 800 pretty hot CPU cores that you can run a program in parallel, that's significant, that's powerful, and you can see how this might really, really improve your productivity if you have a workload that looks like it might be suitable for this sort of construct. If you haven't already, and what I usually suggest to people, depending on what science they're doing, you might look around and see if there's already been a program developed that's MPI capable for whatever science you're doing. It's quite possible that somebody has developed something that'll fit very closely into what you're trying to do, computationally. There's nothing wrong, we can look back at these scenarios that we saw earlier. Let's go. Scenario one, that's Professor Terry's trying to research the migration patterns of the yellow-billed cuckoo. And he's got some Python code, I think is what his is. And what he's doing is he's breaking his data down into 1 gig chunks and then running 200 separate one-core jobs. Well, that works. I mean, there's nothing wrong with doing that. The scalability of it probably is not quite as good as what you'd get with an MPI job, and the efficiency of it certainly isn't. Especially if you're having to do the manual process of breaking your migration data, your data down into fixed length chunks and things like that. In the second scenario, Professor Egson's got an OpenMP threading application, which is great. I mean, threading is a great way to do parallelism. However, she's realized after some months she could probably be doing this a lot more efficiently, and maybe look at a way to either write your own code using MPI, or find somebody who might be doing these similar calculations that's already in MPI capable code they'd be willing to share, or that's publicly available out on the internet. And then we have scenario 3, and we see this quite often. This is one point, I guess maybe the last point I'll make. MPI is not magic. You can't just take a program, throw it on a supercomputer, hit it with MPI, run 1,000, and it's gonna give you this linear speed up. That doesn't happen. You have to put in a little work in order to make a program MPI capable, and if not, you have to put in a little work to find a program that sort of fits into what you want to do that's MPI capable. But hopefully some of the things you've seen today may give you some ideas, or at least spark you down the road to thinking a little bit further, maybe even experimenting a little bit more with your own MPI code. I guess my next steps would be, my next recommendations would be to go ahead and get that, that repository that's out there, download the code, modify it, maybe add your own scripts, look at some of the features that are available in the MPI documentation and see, oh, this one looks like a really good feature. They have all these collective operations, like these all-to-all operations, or I don't know, there's tons of them. Lots of different features that you might find would be a great fit for what you're doing, and just try to experiment with it and see if you can make it work. It's going to take, there's a learning curve, and initially you might find that it's taking a lot of time. But as you begin to use it and become more familiar with the language, the functions, the syntax, it's not nearly as intimidating or challenging as you might think. So again, we do have the code available at either of these 2 links, and you can clone it here. Some resources you might want to take a look at, and again, these slides are available at Auby/HPC train. MPI forum provides, that's basically, they're going to have a copy of the standard there. You can read through. It's really dry and boring, but it might provide something useful. And they do provide these syntactical, function information pieces that you can look at. Mostly I use MPI. A lot of people use MPitch, but I'm recommend that you maybe just take a look at the Open MPI docs and the manual pages available there. There's a website, mpitutorial.com, that has some really good tutorials, code samples that you can just sort of copy and play around with. And then there's a nice tutorial on the Lawrence Livermore Labs MPI page there. So those are just a few things you can take a look at. for the code repository, if you do happen to experiment with your own stuff and come up with your own sort of tutorial type code samples or programs, feel free to, we'd love it if you would, maybe fork the repository, come up with some of your own stuff or suggestions even on the existing stuff of how to make it better, and then do a pull request, and we can collaborate on this sort of thing. And that's usually a good thing to do, and I think it helps further the research along and gets people involved. But I really, at this point, kind of brings me to the end of what I had to say today. I think we had everything blocked till 11, so that's really just about an hour presentation.